All right, let's talk a little bit about energy. All right, because why? Because well, what our plant's going to be absorbing energy, right? Solar energy, and they're going to be converting this energy into a chemical form of energy. So when we talk about energy, we talk about the electromagnetic spectrum, okay? And what is the electromagnetic spectrum? It's going to be a range of all types of electromagnetic radiation. And radiation in this case means energy emitted in the form of waves or photons. So energy travels as waves. Okay, and also could be said it travels as photons. So photons are packages of energy, okay, and these photons travel as waves. Now the way that I want to present it here is I want you guys to basically think about waves, okay? We don't have to go into a lot more detail because this is a biology course, but and it's easier usually it's easier to think about this energy when we talk about light energy, for example. It's easier to look at it as wavelengths, okay, as waves. So the electromagnetic energy travels in waves, like I said before, and the wavelength, okay, is the distance between the crest of two adjacent waves. So the wavelength, for example, if you look at my example here, the wavelength is going to be from crest to crest. Now, why is this important? Because, check this out, the longer the wavelength, okay, the longer the distance between here and here, those waves are going to carry less energy. The shorter waves, okay, in other words, the closer here to here, or the shorter ones, I want to have more energy. And that has to make sense, guys, because this is kind of the big thing, okay? And like, again, just think of them as waves. Again, energy moves as waves, usually in particles, photons, but these photons can travel as waves, okay? So the longer the wavelength, okay, the wavelength from here to here, the longer the wavelength, the less energy these waves are going to have. The shorter the wavelength, the more energy these waves are going to have. Now, there's different types of electromagnetic radiation. We probably knew this, for example, gamma rays, X-rays, UV light, infrared, microwaves, radio waves, okay? And especially this one, which we're going to be focusing on, which is going to be the visible light spectrum. But the visible light spectrum is only a small part of the electromagnetic spectrum. But this is what we use, what plants use to do photosynthesis, okay? Now let me do this in a different color just to follow with a different thought. Okay, I'm gonna stay in this light, but I want to show you something. And again, it has to do with longer wavelengths having less energy and shorter wavelengths having more energy. Let's switch colors here to something like green. Since we're doing plants. Okay, so like we said, increasing wavelength. Okay, as we go from here all the way to here, we increase the wavelength. Okay, so technically these waves here, okay, are going to be the longer wavelengths and thus the lowest energy. And the waves over here, the gamma rays, they're going to have the shorter wavelengths, but yet the highest energy. Okay, now if we overlap this, we use this knowledge in terms here for visible light, which is the important one. Let's see what it means. It means that again, the shorter the wavelength, shorter, and by the way wavelength is abbreviated is usually with a little sign like this. So this means wavelength. Shorter the wavelength, more energy. Which means in this context, in visible light, that purple light here, around purple light over here, around 380 to 400 nanometers, okay, nanometers, these wavelengths are in nanometers. Purple, bluish, I want to have those waves, I want to have the most amount of energy, okay, most amount of energy. Why? Because they're going to be the shorter wavelengths. Now, if you go to the other pole, here we have 750, 700, 750, which 700, 750 means it's bigger than 380 and 400, right? So these wavelengths are going to be longer, so longer wavelengths, okay, sorry, there you go, no, longer wavelengths, and therefore less energy. So light, for example, in the red part of the spectrum, orangey part of the spectrum, they're still going to have energy, but this light over here, around 700, 750, is going to have a little less energy, okay, than if you're talking about the purple color. Okay, now you see when you see visible light, when you have, like, for example, white light, when you put a prism, it kind of breaks it apart into all of these different colors, right? And think about the colors in the way you thing about wavelengths. So purple, for example, purple and blue, they have the most amount of energy because their wavelengths are around 380 to 400 nanometers, right? Green, for example, or tile, something around here is around 500 nanometers. And around here, the purple part, it'll be like 600 nanometers. Then the red and reddest part of it is going to be between 700 and 700 nanometers. Okay, and again, the important thing really is this: the shorter the wavelength, the more energy. So purple light usually more energy than red light, which is still energy, but it has less energy. Now, what do we have to talk about this energy? What do we have to talk about the electromagnetic spectrum, or what do I have to talk about wavelengths? Because let's look at this. Plants absorb energy, right? Plants absorb visible light, okay? Plants are going to be absorbing certain type of wavelengths. Now, how do plants do that? Well, plants have something called pigments. What are pigments? Light-sensitive molecules, usually non-polar. Okay, they're non-polar molecules. They're light-sensitive molecules that capture specific wavelengths of light, and this is very important. Capture specific wavelengths of light. What does that mean? It means that plants have pigments to absorb light, but these pigments, depending on which pigment we're talking about, they're going to be better at absorbing certain wavelengths, okay, certain colors, better than other pigments. Okay, now the most common pigments, and make sure you know that this is important for you to know. I'm going to definitely ask something about this in the test. You have chlorophyll A, you have chlorophyll B, and you have carotenoids. Carotenoids usually are divided into carotenes and xanthophyls. Okay, so there are like three main categories: chlorophyll A, chlorophyll B, and carotenoids. What are these things? These are going to be the pigments. Okay, these are pigments. Now, the absorption of light is usually mostly around the blue range over here, okay, and the red range around here. And this makes sense why. Okay, let's look at this. Just look at this one over here, okay? Let's look at this graph, okay, to be able to understand what this means. And it's actually very easy once you understand this topic, okay? So here we go, guys. Here we go. I'm gonna go step by step. What is this graph telling you? Well, y-axis, the absorption of light by chloroplast pigments. Now there's three pigments here, right? Chlorophyll A, chlorophyll B, and carotenoids. Okay, and this is telling you how much is being absorbed. What's in the y and the x-axis? The wavelengths of light that are being absorbed. Okay, so far so good. Okay, now let's go step by step. Now when I erase this again, I'm going to erase this part here. I'm going to focus on chlorophyll A. Chlorophyll A is what? It's a pigment. Very good. I don't know why I put a G. I don't need to put a G. Chlorophyll A is a pigment. Okay, that absorbs best where? Let's look at the graph. Let's look at the absorption of light in chlorophyll A. I'm not using red to give some contrast. It's going to be this one. And what's happening here? What do we see here? We see that the most amount of energy, okay, of wavelengths captured by chlorophyll A is around here. So we're talking about maybe around the 450 range, right? Which is kind of the purple part of the spectrum. Now this is a clear. This is a kind of the mountaintop, right? That means that most of that means that chlorophyll A is really good at capturing these wavelengths of around 450, okay, um, around in the purple blue type of the spectrum, and then its capacity to absorb light kind of just goes down, right? And you're thinking, okay, that's it. No, 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 that's not it. Look at this. What does this thing go? Why am I going down? It's saying that chlorophyll A is not very good at absorbing other colors, like for example, green, for example, yellow. How do I know this? Because look, I'm way in the bottom, right? Right in the basement here. But what happens at this part? Suddenly chlorophyll A becomes really, really, really good. And I don't know what the heck I'm doing here anymore. They get really, really good, okay, at also absorbing wavelengths of around, I don't know, let's say 670 maybe. I'm just approximating, okay? But around the kind of the red orange portion of the spectrum, right? So chlorophyll A is also really good at absorbing these wavelengths. And then again, it collapses around the red part. Okay, it collapses. So what is this telling us about chlorophyll A? Chlorophyll A is really good at absorbing certain wavelengths. In this case, around 450, around 670 maybe. And not only that, but we can also say, or I may ask you like this in a test, chlorophyll A is really good at picking up the purple color or wavelengths around the purple color and around the orange red part of the spectrum. So far, so good. Okay, I'm going to erase this, so please feel free to pause it. I'm going to do this in a different color. I'm going to do this blue. Chlorophyll B. What is chlorophyll B? Another pigment, right? Now let's follow chlorophyll B. This for this absorption spectrum. Okay, so this absorption of light. Okay, of chlorophyll B. What happens here? It doesn't really capture very well. It does capture light here. Okay, it does capture. You can see it's going up, 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 up until it gets here. This is going to be like the top of the hill, right? This is the part where, or this is the spectrum. This is the wavelength at which chlorophyll B absorbs the most amount of light, or is best at absorbing this wavelength. Okay, I'm talking about, I don't know, around 400 and maybe around 460 or something like that. Okay, again, it's an approximate. I'm just approximating from my from the wavelength of light over here, around that. But I would say chlorophyll B is really good at absorbing around the blue part of the spectrum, right? Around this blue light is going to be, chlorophyll B is really good at capturing this type of this light, the blue light. Okay, and then what happens? Then it crashes, right? Just like it happened before. So what does it mean that this crashes? It means that chlorophyll B, as we go down, as we go down the spectrum here, we go down the spectrum here, it's getting worse and worse and worse and worse and worse at absorbing things. It's pretty much as bad as my drawing right now, right? Okay. So, and it goes down, and it goes really down. And can it absorb the wavelengths around the green color? No, not really. What about yellow? Yeah, very, very little. Okay. And then it kind of gets a little bit good, okay, when it gets to the kind of the orange part. Okay. Here is going to be another part, another little cliff, another little mountaintop where chlorophyll B is really good at somewhat good at absorbing. So chlorophyll B is also pretty good at absorbing light around, I don't know, 600, and I'm gonna say like around 600, and what do you think? 600, maybe 640. Again, approximate. Okay, around the kind of the purple part of the spectrum. Okay, purple. The sorry, not purple, but the orange part of the spectrum. Okay, and then again it collapses. That means it's not very good at absorbing red light. Okay, so far so good. Let's do one more. I'm going to erase this again. Use a different color. Let me do purple or fuchsia. Orange, actually. There you go. Carotenoids. Okay, carotenoids are gonna be again, what are they gonna be? They're gonna be pigments, right? They're gonna be pigments that absorb light best around this part of the spectrum and this part of the spectrum, right? So around, I don't know, 400 and maybe 450 or 60 more or less, right? More or less, and around maybe 480 more or less, right? So carotenoids are really good at absorbing these lights, okay? It's also okay absorbing these lights. I mean, it's not that bad, right? It absorbs a little bit of purple, a little bit of blue, and actually it's kind of good, the blue part here. And then when it goes to the green light, ooh, it collapses just like everyone else. But then this one doesn't have any more, okay? It's just carotenoids are only kind of good at absorbing around this part of the color spectrum, okay? Great at absorbing kind of purple, blue, and kind of the blue part of the spectrum, and not very good at the green. Okay, and definitely not good at picking up orange or yellow or red at all. Okay, the light does not be able to pick up the pigments. So hopefully what you get to see from here is this. We have a lot of different pigments, or plants have a lot of different pigments that make it a bit that makes it I'm gonna say this. There's so many different pigments that makes plants pretty good at capturing different types of wavelengths, right? Not just in the 400s, not just in the 500s, but it's able, because it has different pigments, to be able to capture wavelengths in the purple part of the spectrum, in the blue part of the spectrum, in the kind of in the green part of the spectrum, and also allows them to pick up some light over here. Okay, and that's the whole thing, and that's why it's important, because, well, what is one of our main ingredients of photosynthesis? Light. The more light you have, guess what? Or the more wavelengths we have, guess what? Well, the better you will be at doing photosynthesis, right? Now, if you look at my other picture here, I'm going to overlap this really quick. If you look at this picture, what is this picture of this graph telling you? Y-axis is the rate of oxygen production. This is how we get to see the production of photos, or the rate of reaction of photosynthesis. Okay, where does photosynthesis occur best, or which lights, or which what wavelengths? Because this is going to be the wavelengths over here. Which wavelengths able to give you a better rate or higher rate of photosynthesis? And you know what? I don't know if you noticed this, but this, okay, this looks almost exactly as this. Why? It's telling you different things, guys. It's telling you the rate of photosynthesis using oxygen production. Why? Because oxygen is one of the products, right? So you measure the amount of oxygen produced, and that's how you measure the rate of photosynthesis. Why do we get a very similar graph? Because, as we saw, most of photosynthesis, okay, most of the pigments are able to absorb around this part of the spectrum, right? Same thing over here around this part of the spectrum, you see, around the purple, blue, green part of the spectrum. So because we have a lot of pigments here in this part of the spectrum that's able to pick up sunlight in good amounts, so we get to see more photosynthesis. Now let's see, what about over here? There's also a lot of photosynthesis happening here, right? And what does that make sense? Because here we also have some pigments, right, that are able to pick up light in the wavelengths of orange and red, a little bit of yellow, right? And that wavelengths are, there's pigments that we can pick up some light. Therefore, we have light to be able to do photosynthesis. But then guess what happens over here? And this is kind of the funny thing, right? This is kind of the big thing here. What happens in B? Do you see photosynthesis? The answer is yes, you do. I mean, you do see a little bit. You know, you do see some photosynthesis. If you look at the graph here, you do see some photosynthesis, but not as much, right? Why not? Because this is part of the spectrum. This part of the spectrum is this part of the spectrum, when there is not a lot, when pigments are not very good at picking up those wavelengths. Okay, plants are not very good at picking up the green color. Okay, and here comes to one of the things I want you to learn, and you can apply everywhere else, right? Why are plants green? I'm gonna start like this. Why? Let me do this in green. Let me do this in green. because plants don't or can't absorb green light. Okay, simple as that. Because plants cannot absorb green light. Therefore, if it cannot absorb it, plants reflect the green light. Okay? Simple as that. So there's two things that are going to happen here. If they're not absorbed, they're going to be reflected. So why are plants green? Because green, as you can see over here, you can see one of the graphs here, green is not absorbed very well. Because it's not absorbed, it's going to be reflected. Okay? If a color is not absorbed, it's going to be reflected. So for example, if you have a red shirt, let's talk about if you have a yellow banana, right? What colors are being absorbed? What colors are being reflected? Now, if you understood this with the plants, then you know that in the yellow banana, all wavelengths are absorbed. All of them are absorbed except for yellow. Yellow is being reflected. The color that is reflected is the color that you see. Okay? Hopefully that makes sense. And that, ladies and gentlemen, that is kind of the big deal about light, about energy. Energy travels in waves. In this case, we see that waves can be waves are usually seen as usually measured as wavelengths. Okay, and part of the electromagnetic spectrum, you have visible light, which is used in photosynthesis, and these wavelengths, some of these wavelengths in the visible light are able to be absorbed, some others are not, some of them are absorbed, some of them are going to be reflected, and these light needs to be able to be absorbed by pigments, okay, because that is how we're going to be able to do photosynthesis, because photosynthesis requires energy.